The ideal gas law. So we can take Boyle's law, Charles' law, and Avogadro's law and combine them all into one law. And it's called the ideal gas law. And it's generally expressed as PV equals nRT, which people sometimes pronounce pivnert. So there's pivnert. So what are these letters? Well, we've seen PV, N, and T. What's this R business? R is a constant. In order to take these proportionalities and make it into an equality, there is a constant. And it turns out that this is the same for all gases, so it's called the universal gas constant or the ideal gas constant. So R is equal to 0.0821 liter atmospheres per mole Kelvin. Very, very messy unit, but also very helpful because it tells us the units that our other things have to be in. We need liters. So volume has to be in liters, pressure has to be in atmospheres, amount of gas has to be in moles, not in millimoles or in grams or anything else. Temperature has to be in Kelvin. So that's all down here. But it's hiding right there in the ideal gas constant. And I'll give you that constant. It'll be in the helpful information for the exam. This table kind of goes over how all these gas laws are related. Some of you might find that interesting. Here's another one that we didn't look at individually, Gay-Lussac's law that relates pressure and temperature. So you can take any two variables and have a relationship between them. The ideal gas law allows us to calculate things when we don't have changing conditions. So here we have a question. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. So sometimes it's a little hard to know right at the beginning where you're going to end up. What direction is this going to go? What do I need to do? So you can always make a table. We'll find out with this problem that we don't really need to make a table, but it's not going to hurt anything. So for these gas law problems, making a table is always a good idea. So we're going to make a table, 1 and 2, just like we've been doing. Volume, calculate the volume. Okay, there's no number there. We'll ignore that for now. We're looking for numbers. 0.845 moles. 0.845 moles. And what variable is associated with that? N, right? Number of moles. Pressure of, okay, so they came out and told us that was the pressure. There's the pressure. And a temperature of 315 Kelvin. Oh, they were so nice to us. They gave us the temperature in Kelvin that time. We are out of numbers, right? There's nothing for the bottom part of the table. That's okay. Turns out we didn't need the bottom part of the table. We'll just get rid of it. Did it hurt anything? No. I've now got all my numbers nicely labeled. This is N, this is P, this is T. When you don't have 2 rows in your table, you're going to use the ideal gas law. So the ideal gas law, PV equals nRT. What are they asking us for? The volume. So volume. I need to rearrange this the same way I did with the other gas laws. We'll divide by P. P's cancel out. Have to do the same thing over here. So volume equals nRT over P. So N is 0.845 moles. R. Oh yeah, that was on that previous slide. You might end up memorizing it because you're going to use it a lot. 0.0821 liter atmospheres per mole Kelvin. Yes, it's tedious, but write the units in anyway. 315 Kelvin. Divided by the pressure. Oops. 1.37 atmospheres. Before you get your calculator out, look at the units and cancel them out. So here I've got moles canceling moles, and kelvins cancel kelvins, and atmospheres cancel atmospheres. And I've got left the unit liter, which is a unit of volume, which is what I'm trying to calculate, so that's a good sign. If you check your units, you might realize, oh shoot, I've got my volume in milliliters, or I've got my pressure in millimeters of mercury. I need to fix that. So now we can calculate 0.845 times 0.0821 times 315 divided by 1.37 equals, come on, volume equals, let's see, we got 3 sig figs going on here. It's going to round to 16.0 liters. Calculator says 15.951071117. Any questions? This is an example of what we're going to be doing next week in lab. By measuring the pressure, volume, and temperature of a gas and the mass of it, we can calculate the molar mass of a gas. So let's look at this one. A sample of a gas has a mass of 38.8 milligrams. Its volume is 224 milliliters at a temperature of 55 degrees Celsius and a pressure of 886 torr. Find the molar mass of the gas. And this is the sort of problem that probably could make your head spin on an exam because you're like, oh my goodness, where did that come from? Just start thinking about it. Well, molar mass. What is molar mass? We abbreviate it capital M, molar mass equals it's grams divided by moles, right? It's the mass of a substance divided by the number of moles in that particular sample. Well, what are they giving us here? They gave us the mass. It's not in grams, but we could convert it, couldn't we? 38.8 milligrams, and we want milligrams on the bottom and grams on the top, and milli means 10 to the minus 3. So this is 0.0388 grams. So the molar mass is the number of grams divided by the number of moles. Are they telling us what the moles are? They don't come out and tell us, but they give us pressure, volume, and temperature of a gas. PV equals nRT. We want to know what N is. We can use the ideal gas law to find the number of moles of the gas. So I'm going to rearrange this. I'm going to divide by R and T this time. So those guys cancel out. And then that's the same over here. So I've got N is equal to PV over RT. Now, in this problem, they were not kind with the units. All the units that they gave are not quite right. R is 0.0821 liters times atmospheres divided by moles times Kelvin. This tells us what units we have to have. What pressure did they give us? 886 torr, which is the same as millimeters of mercury. Can we convert that to atmospheres? Sure we can. The relationship is 1 atmosphere is equal to 760 torr. So 886 divided by 760. It's going to equal 1.1657. It really only has 3 sig-figs. And the temperature needs to be in Kelvin. They gave it to us in Celsius. Temperature is 55 degrees Celsius. We'll just add 273 to that. 328 Kelvin. And the volume is also not quite right. I wrote the answer. It's showing on my iPad, and it's not showing on the computer. Look, see? Come on, put it up there. Very strange. See, there it is right there, 328K. That's bizarre. I'll just have to write it over what I already wrote. Okay, whatever. You're scaring me. Volume. 224 milliliters. What does it need to be in? Liters. So we need to divide by milliliters, multiply by liters. Milli means 10 to the minus 3, so we stick that up here. Units cancel out. We get 0.224 liters. Now we have everything with correct units, so we can plug these things into the equation. 1.1657 atmospheres, that has 3 significant figures, times the volume, 0.224 liters, divided by R, 0.0821 liter atmospheres per mole Kelvin, times the temperature, 328 Kelvin. So N equals 1.1657 times 0.224 divided by 0.0821 divided by 328, 0.009696563. That's a small number. Don't let that scare you. Sometimes numbers are small. How many significant figures should that number have? 3. Remember, these leading zeros don't count, so 969. So I'm going to carry 2 extras into my other calculation. Because remember what we were doing? We were trying to find moles so that we could stick it in up here. So I'm going to put in 0.00969 66 moles. I rounded it. So now I've got 0.0388 divided by 0.00969 96966. And this should have 3 sig figs, and I come up with 4.00, and the units are grams per mole. What gas is this? It's helium. Helium has a mass of 4 grams per milliliter. Can you have a substance with a molar mass less than 1 gram per milliliter, gram per mole? No, you can't, because hydrogen is the smallest element. It has a molar mass of 1 gram per mole, but it doesn't hang around as atoms, so its molar mass is actually 2 grams per mole. So if you come up with a molar mass that's less than 2, something went wrong. So I'll see you guys on Tuesday.